Should I start? Okay. Good afternoon, everybody. It's a big pleasure to me to introduce today Remco van den Bosch, coming from the MPA. So Remco did his PhD in Leiden under the supervision of Tim Dessous, who was here very recently. And then he moved to Texas. He was a McDonald Fellows in Austin, where he was working with Carl Gerhardt. And after that, he moved to Heidelberg, where he has been for 3 years and a half, where he's currently a research scientist there. And his work has got recently quite a lot of attention with the publication of a Nature paper on the galaxy NGC 1277, a compact relic galaxy that most of you know, where he found evidence for this galaxy having a overmassive black hole. So today he would be talking about this type of galaxies and the survey he's conducting on these quite interesting objects. And, well, thank you very much. Go ahead.
Thank you. Well, it's good to be here. Today I'm going to go talk about, most of the time, about how galaxies and black holes interact, or how much we know about what kind of black holes belong to what kind of galaxies. This is one of the classic examples that people always show. This is Sen A, where you can see the black hole in the center blowing out big bubbles and clearly interacting with the galaxy. One of the things that people always think about when they talk about black holes and galaxies is that the black holes and the bulges correlate with each other. So the bigger the bulge in the galaxy, the bigger the black hole is that you see in a galaxy. And this is the classic plot that everybody always refers to, which is now quite old, which is from Herring and Rich from 2004. Which shows the bulge mass of the galaxy versus the black hole mass of the galaxy, and they seem to be perfectly correlated with each other. And so this is, for a long time, as people sort of kept repeating over and over that, well, bigger galaxies have bigger bulges, and so they have bigger black hole masses. And this sort of ties in with sort of like different galaxy types. So this is one of the newest Hubble tuning forms. This one is from Cormany from 2 years ago. And this essentially shows a sequence from like disky galaxies with different sized bulges to early types on the left end. And so the idea that people have of this is that the bigger bulges have bigger black holes. All right. But there's lots of complicated stuff with this that don't directly make sense. So one of the really obvious things is that we find quasars of redshift 6 and 7 that seem to appear to have 10 to the 9 solar mass black holes. Clearly, these galaxies don't have a 10 to the 12 early type around them at that time, because they don't exist. So somehow those black holes came before the galaxy. One of the obvious ways to show this, as well as this is from the Sloan on the left. So it shows redshift versus black hole mass of AGNs detected. And you can see that as a function of redshift on the left, the black holes that you see accreting mass actually become smaller and smaller black holes. So we see the biggest black holes accrete mass at very early times, and we see small black holes accreting mass today. So somehow this already indicates that the biggest black holes formed early and the smallest black hole are still forming today. The plot on the right essentially shows you an inversion of the AGN luminosity function, and that essentially shows you the same things where the different colors are different redshifts. And then so the x-axis is black hole mass, the y-axis is the space density. And you can see that at the right that there's essentially no evolution for the most massive black holes at high redshift. They essentially just don't change. So the biggest black holes form very, very early, and at low redshift, the new black holes are forming. And so there's lots of ideas on how the black holes in the galaxies co-evolve. I'm going to go through 3 of them just to quickly give you an idea of what kind of landscape we live in. The first one is a very simple one where they just say, well, there's an equilibrium between the gas density and the stuff you can accrete in a black hole, and this means that if you will always end up with a black hole mass that scales to the galaxy dispersion to the power 4. Just because it's an equilibrium, and at some point you end up having so much feedback that you can't accrete anymore, and then you're done. So that's how you end up with a scaling relation between the bulge galaxy and the black hole. The other thing which is typically invoked is through merging. Right? This is a very old movie, but the idea here is still essentially the same. You have 2 galaxies that merge. What happens during that merger is you have a whole bunch of gas fall towards the center, which helps you build a bulge. But at the same time, will actually feed the black hole. And once you start feeding the black hole, you end up making a lot of wind, and you blow out all the material that can create on the black hole. And so this is how you then end up with a bulge mass that is related to your black hole mass. So here the feedback is turned on, and you blow away all the gas, and you can't accrete anything onto the black hole anymore. All right, fine, that works. And then there's the really simple one that just says, well, if I just start out with a random distribution of black holes and bulge masses, and I just merge and do n mergers, then over time, there's actually going to be a relation, because it's actually just not a minimization, but just the number of mergers just gives you a relation between the black hole mass. So this is shown here. This is from a paper from Janken and Andrea Macho. The blue box is like an initial distribution of bulge masses or galaxy masses and black hole masses, and then the red line is after, I think it's like 10 redshift 10 to now evolution. You end up with a scaling relation because you just merge a whole bunch of times and you just collide everything together. The cute thing about it is that these three theories all have very different predictions on what you expect today for the black hole relation between the galaxy and the black hole. So if it really is the black hole feeding with the equilibrium through the gas pressure, then you just have no scatter whatsoever. It should just be set. If it is through merging, then you would expect galaxies with big bulges that clearly have had a merger to have bigger black holes. And if it's the number of mergers, then the thing you expect is that the scatter decreases with the number of mergers that you have. So you would expect a very tight relation for the galaxies like the BCGs in the center of clusters to have a very well-defined black hole mass, and galaxies that have only seen few mergers to have a much larger scatter. All right. So what does that plot that I started with in the beginning, what does it look like today? So this is two papers from last year, essentially the same data but different interpretations. On the right is from the Cormier and Ho review from 2013. The different colors indicates ellipticals, classical bulges, and pseudobulges, and this is the distribution of bulge mass versus black hole mass. On the left, it's the same thing. It's pretty much exactly the same data points, but instead of having one line, these authors preferred to have a break in it. So this is, and it's nowhere near as clear that there's a clear relation as in the plot in the beginning. And so this is just, it's about 10 years of evolution in this plot, and it's not really obvious anymore that there's a direct one-to-one relation between these two quantities. What makes it even worse is if you do, instead of bulge mass, you just do total luminosity. So this is from a paper from a postdoc in our group, or Lusker, who did, on the right, it's total luminosity. On the left, it's bulge luminosity versus black hole mass for a subset of 36 galaxies. And essentially what he shows is that it doesn't really matter whether you take bulge mass or total luminosity. The relation is sort of equally good. So it's not necessarily bulge mass. It could just all be total luminosity. All right. So what do we do? Is M sigma any better? Sorry. This is the newest M sigma. So if it's not bulge mass, could it be dispersion? So this is sigma again. The color here indicate early types versus classical normal bulges. And you can see that, especially at low dispersion, there is now a large amount of scatter in this relationship. And you should be a little bit worried if you use your M sigma or your scaling relation in your picture of galaxy evolution, then you need to be a little bit worried about how this all checks out. The other thing to realize is that this M sigma is used all over the place, right? If you get an AGN and you want to measure its black hole mass, people use either reverberation mapping or they use the other luminosity things. But they're all directly dependent on this M sigma. So they take their distribution of reverberation mapping. So on this plot here on the left, all the blue points are reverberation mapped AGN. All the red things are the locally determined, directly determined black hole masses. And they have to sort of line them up. They have it's not the scale factor, but it's a slope that they sort of fix to the local early types. And you need to realize that this is actually like a fairly scary game. You plot these two things together, the thing to realize is that all the reverberation mapped AGNs have very low dispersions, whereas most of the black hole masses that we've been measured on seem to lie in that relation, lie on the right of that green line, right? So it's not really obvious that it's that clear-cut that we can directly do this. I'm not saying that the reverberation black hole masses are wrong. I'm just saying that this is a caveat to keep in mind. All right. So why are there so few direct black hole mass measurements? And this is actually a very important thing to remember. To actually directly measure the black hole mass, you need to actually resolve, spatially or somehow, resolve the region in the galaxy where the black hole mass has the most influence on the gravitational potential. Otherwise, you cannot directly measure what the black hole mass is, right? So you need to resolve that region on the sky. For a 10 to the 8 solar mass black hole at a distance of 10 megaparsec, this resolution is about 0.2 arc seconds. For a 10 to the 6 solar mass black hole at 1 megaparsec, the sphere of influence is 0.1 arc seconds. So we can only measure a black hole mass of 10 to the 6 solar masses with optical or near-infrared telescopes today only out to 1 megaparsec. How many galaxies are there out to 1 megaparsec? Not very many. And so what ends up happening is that most of the black hole masses that have been measured are for galaxies that have high dispersions, because a higher dispersion gives you a larger sphere of influence, because the black hole mass goes up with power to the 4, the sphere of influence drops off with power to the -2, so you end up preferring galaxies with the biggest dispersions. All right. The other reason why this is hard is that you actually need a lot of data. You need to resolve the amount of stars near the center near the black hole, so you need HST imaging or something better. And typically you can't really use AO imaging because you actually need to know what the PSF is to be able to figure out what the mass distribution is. You need to get adaptive optics or STIS spectroscopy near the black hole. And because the pixels are so tiny, this takes a long time. So this typically is 4 hours of exposure times with an 8-meter adaptive optic systems. And that doesn't even count the overheads. And you also need large-scale kinematics to be able to constrain the stellar mass to light ratio. So to measure one black hole mass, to do the one direct one, you need to have 3 data sets, you need to get them all matched, and you need to do some dynamical modeling, which I'll get to a bit later. And so this is a fairly big computational effort. And so before you want to go do this and oh, instead of we have done 80, we should do a whole bunch more, you want to make sure that you can actually know which galaxies you should do this for. And so when I was in Austin, we were trying to figure out, hey, which galaxies can we actually do? And we started a little project on the Hobby-Eberly Telescope, and we were trying to figure out, so we had about 60 galaxies with the higher dispersions, and we were like, well, we're going to go do those, to just get long slit spectroscopy to figure out if these dispersions were actually right. Because a whole bunch of these had literally dispersions of 500 kilometers per second, and we didn't believe it, and so we're going to go try this out. And so this little project turned out to be a very, very good project for this telescope. So this telescope is actually kind of peculiar. It can only rotate around this axis. It can't go tilt up and down. And so this means that at any given time, it can only actually look like on a donut on the sky. And so if you have a whole bunch of targets that you only need short exposure times for, you can essentially have a really nice backup program for this telescope for when there's the seeing is not good, or when they don't have a specific target to do. And so they ended up giving me about 550 hours to do this project in the end, because I just used over 3 years, I used a lot of their bad weather time, as they call it, which was great because it's a 10-meter mirror. I'm looking at very bright nearby galaxies. In 15 minutes, I can get a really good, decent long-slit spectrum. It's awesome. So the telescope went down for an upgrade last year, and they stopped giving me data, which is great. At some point, you have so much data, you don't know what to do anymore. But the main thing about this survey, the thing that we did was we were trying to find all the galaxies for which you could possibly do black hole masses. So essentially, I was trying to get all the nearest version of whatever type of galaxy I was trying to get all of this. So if you have a favorite galaxy, I probably have a long-slit spectra for it. The paper is about to be submitted. I want to make the data as public as soon as possible. So if you have a direct need for it, let me know. But otherwise, it's going to be on the web in a couple of weeks. Anyway, so let me show you a little bit more specifically what's in this survey and how they were selected. The obvious first thing to do is just use M sigma to predict the sphere of influence. So you use the M sigma relation. You take a literature dispersion from hyperlate or Sloan or whatever, and you just plug that in to get a black hole mass. Then with that black hole mass and the distance, you can predict the sphere of influence, and you end up targeting it. So the plot here on the right are the galaxies that are targeted. The gray background is the galaxy in the database with literature dispersions. All the green ones are the ones that are targeted. One of the things that is very interesting, which of course I said earlier, but is clearly obvious in this plot, is that at high dispersions, the galaxies have higher predicted sphere of influences. So these are the ones that you are more likely to be able to do a black hole mass for. And there's not very many at low dispersion. The other thing to notice here is that there's actually not that many. It's about 100-ish that you sort of predict that you could do this for. It's not that many. Anyway. But also important, a lot of galaxies do not have velocity dispersions in the literature. So you need to somehow predict what the velocity dispersion is to get a black hole mass estimate. Luckily, there is two-mass imaging over the whole sky, and you can do a fundamental plane fit through the the two-mass photometry. You can actually predict the dispersions quite accurately. I have a plot of this over here. And so this is just based on the two-mass stock data, you can actually predict the dispersions quite accurately to about 0.09 dex. It's kind of cute how well that works. Again, in both these plots, the green crosses are the galaxies that I've actually observed. The other thing that I did was not only do the biggest sphere of influence galaxies. The other thing that I tried to do was just to fill out the parameter space. So try to find the biggest galaxies, the smallest galaxies, and everything in between. And I would always pick the closest version of whatever type is visible. So essentially, I don't only have the highest sphere of influence galaxies, but I also have the galaxies with the biggest galaxies that are closest by. And so whatever scaling relation you want to use for the black hole mass, I always have whatever type in size, whatever. Then I always have a galaxy in the survey, hopefully. All right, so what does the final distribution of sphere of influence look like? Just assuming the m sigma as the scaling relation, this is what you end up with. So this is, with my dispersions, this is then the distribution of galaxies for which you could possibly do black hole masses, which is interesting, but it's not, well, useful, but it's not actually interesting by itself. A little side note on the stellar kinematics to show you that I'm not completely bonkers in what you're sort of going for. This is just an example of two spectra over two different galaxies. The top one is a galaxy with a very low dispersion. The bottom one is one with a very high dispersion. And you can clearly see, this is essentially how you measure the stellar velocity dispersion. You can see the Doppler broadening of these lines, and you can actually see, in this case, it's really obvious what is a high dispersion, what is a low dispersion. An important note here is, so I've clearly compared my velocity dispersions with the literature dispersions. So the plot on the left is Sloan versus me, and you can see that there's a really nice one-to-one correlation, and I actually get my dispersions right, if you believe the Sloan dispersions. In the middle panel, you see my comparison versus Hyperlata. And the Hyperlata database is a fantastic resource that has for a long time cataloged a lot of data on nearby galaxies. And they also have dispersions, but a lot of their dispersions above 300 kilometers per second are clearly wrong. And this is mostly because these were taken from different literature sources, and very often when they get a high dispersion, there's something that went systematically wrong with the data reduction and stuff. And so if you just trust that database to sort of pick a good target to do a black hole mass, you pick one with a really high dispersion, but very often you end up picking the wrong one. The plot on the right shows Sloan versus Hyperlata, and you see the same effect for galaxies above 300 kilometers per second. Most of the Hyperlata ones are just off. So this is where it gets cute. So you have this sample, and then you can start doing cool science stuff. So here is just a distribution of galaxies. All the green points are my data points for my survey. So this is x-axis is velocity dispersion. The bottom y-axis is luminosity, and the top one is half-light radius. And one of the really cute things is that in my survey, I have more high-dispersion galaxies that are small than high-dispersion galaxies that are large, which is curious because you normally think that the biggest dispersion galaxies should be big BGGs, big early-type galaxies that have large dispersions. That's how you think about galaxies, but not so much in the local volume. So in this plot, this is taken within 130 megaparsec box, just essentially just everything that's in there that has a dispersion, and the galaxies with high dispersions, the biggest ones are the galaxies with the highest dispersions are actually small galaxies, not big ones. And so what do they look like? These are two examples. I'll get to possibly these galaxies a little bit later as well. These are little tiny disks that rotate very fast and have really high velocity dispersion peaks. So the plot here on the two panels, the top shows you the rotation curve, the bottom shows you the velocity dispersion along the slit. And these two galaxies are both 1 kiloparsec and have weigh about 10 to 11 in stellar mass. And these galaxies don't, if you look at if you plot them in a luminosity size plot, they don't stand out. They just lie on the main locus, you don't notice. But the only reason they stand out in this plot is because they have a very high dispersion. let's look at this in a little bit more detail, but in context of other galaxies. This is the Perseus cluster, and this is dispersions of the galaxies in the Perseus cluster. So you have the big BCG, which is a big, bright, booming AGN, energy 1275, has a dispersion of about 290 kilometers per second, which is exactly what you sort of expect for a big early type. This is by far and away the most luminous galaxy in this cluster. You can't see it because it's very extended, and so you don't see it as much in this plot, but it's by far and away the most luminous galaxy. You have a little spiral galaxy all the way to the right, which only has a dispersion of 64 kilometers per second. Hey, this all makes sense. And then you have these two odd ones, NG 1277 and NG 1270, which are tiny galaxies which have dispersions of about 400 kilometers per second. It's just, yeah, crazy. This is why these things are just so odd. And so this is where I ended up being incredibly lucky. NG 1277 actually had a HST image because there was a mispointing of HST. And it was supposed to point to the north part of 1275, and it missed by a little bit, and so there was an image of 1277 sitting in the archive just for me. That's what it looks like. So this is a tiny little disk galaxy that you can sort of figure this out. And now I'm going to walk you through how we actually get to measuring the black hole mass in this system in a little bit of detail. So I have the image, so that tells me where the stellar mass is. Where the stars are, and I have the long slit data, so that tells me the stellar kinematics, so that's what this looks like. So the top, again, is the rotation curve, so this has a rotation amplitude of 300 kilometers per second, and then a dispersion peak that goes up to over 400 in the center. And we need to go through a whole bunch of steps to actually measure the black hole mass. And this is done using an orbit-based technique that's been used for a whole bunch of papers. I'm not going to go through the list, but you can look them up later. The first thing that we need is we need to have a trial potential. And so to make the trial potential, we first need to turn this image into a mass model of the stars. So this ends up being, we do this with either Galfit or Mikhail Kaplar's IDL code to do this, but you can essentially just fit Sursix or whatever and make an MG out of this. And this is what it looks like. So this is a mass model of your image. Essentially, this is a two-dimensional analytical representation of your galaxy. You take that, you assume an inclination, you make a three-dimensional distribution of your stellar mass. You add in a black hole mass, your dark matter halo, and whatever other prescriptions you want, and you make a trial potential. In that trial potential, you can then start integrating orbits. This is an example of one orbit in one of those trial potentials, and this movie is sped up logarithmically over time, and you can see that it actually covers a very clearly defined pattern in this space on the sky. And so you can clearly seeing it building up nodes, and it actually is a very regular thing. You can see this is sort of disk orbit, and it typically builds up like 4 nodes that become most luminous. Anyway, so one orbit is of course not enough. You build a whole bunch of these things, and this is an example again of that same potential with a whole bunch of orbits. And the one on the top left is my favorite. You can see it come close to the black hole and then go loop around. See how that works? Gets close in. The one on the bottom left is like a polar orbit. What? Oh, the scales. So this is the scale of this image. Oh, I used to have a slide that had it on it. Essentially, the orange ring is about 2 half-light radius, which is about 2 or 3 kiloparsecs. So this image goes out to, it's about 10 kiloparsec from the center. Oh, the orbits here are the same scale as that image, yeah. I'm going to put them onto the galaxy in a second. So this is a cute thing. You know that polar orbit is way too round to actually be in this galaxy. The one that goes close to the black hole and goes around doesn't fit any either. So you get these 2 other ones that actually fit into this, and you can sort of put that on, and you get something. This is then one example of how this sort of fits. So this is to get your scales. The cool thing about it is that the way this works is you end up having you need to pre-compute a whole bunch of orbits, and then you put them all together to figure out how to reconstruct your mass distribution, your stellar mass distribution, and at the same time you need to fit your stellar kinematics, right? So you have this complicated jigsaw puzzle, which luckily the computer solves for you, but you can just try different trial potentials and see which ones work out, and then you end up, by doing this in the end, you also know what kind of orbits are actually in this galaxy, which is kind of fun. So this is then showing the total model fit. You have your observe stellar kinematics. I have the line is now the fit to the data, and you end up having you end up getting a fit to your mass distribution. And to show you sort of how this goes by changing the black hole mass, I have this plot as well. So here on the right, I show two different models. The black line is the best fit. The dashed dotted line is a model with a 10 to the 8 solar mass black hole. And you can see that one does not reproduce the data. And so this is the best possible model with a 10 to 8 solar mass black hole, and then change the mass-light ratio to get the best possible fit in the dark matter halo. And this does not fit at all. If you change that from 10 to the 8 to 10 to the 9, it gets better, but you still don't get that high dispersion peak, and you don't. So you can see it trade off, right? This is the cool thing. You can see that it increased the mass-light ratio to get the dispersion rate, but that still means that it over-predicts in the outer parts and under-predicts in the center. Anyway, on the left, right, you see the contours of black hole mass versus mass-light ratio with like 1, 2, 3, 4, and 5 sigma. And you can see that you get a really well-constrained black hole mass and mass-light ratio from this particular data set. But obviously, this is long-slit data taken on the bad weather conditions, and I'd rather show you IFU data, which is more fun. This is the same thing. This is NC 1277. Again, the top is the observed rotation field. This is PPAK IFU data. And the bottom is the model of that same data, and then the bottom left is a mass-light ratio versus black hole mass. And the cool thing about this ends up being the black hole mass is about 9.9 log 10 to log black hole mass, and the mass-light ratio is about 7.5-ish. And this is really cute. You have a 10 to the 10-ish solar mass black hole in a galaxy that weighs 10 to the 11 in stars. So you have a black hole mass that weighs 5 to 10% of the actual host galaxy. It's a humongous black hole in a very, very tiny galaxy. How does that work? And to sort of give you more details on how odd this galaxy is, so this is showing you the orbital structure. The movie shows you the orbital structure of this galaxy, so you can see the stars. The red star in the center gives you like how fast the star goes because of the black hole in the center. Then you have the green one is the galaxy, the disk that you can see rotating around. And then the blue one at larger radii lives in a dark matter halo, and you can see that go up and down because that lives in a much rounder dark matter halo. So you can actually see how the dark matter halo affects the potential. The cute thing about it is there's no non-rotating bulge component in this thing at all. Right? So if you want to make your black hole connect to a dissipationless thing that formed through mergers and that kind of stuff, then this does not work. This clearly did not happen for this thing. The other thing that's odd is that this thing has a very high mass-light ratio, so this is clearly an indication that this thing must have a bottom-heavy IMF of some sort. This thing is also very old, which means that this thing formed a long time ago. And remember that at the beginning I said that from the quasars are very high redshift, we know that all the black holes then already 10 to the 9. This thing was probably around back then. The black hole was, and the galaxy must not form much later. There is a little bit of X-ray flux that's sort of consistent with that black hole mass, given some accretion rate. But yeah, the way that you still make this, there's lots of different possibilities to go through this. And this is also worth showing, but that came with the point that I just mentioned. The stellar ages of this thing just don't vary much as a function of radius, and it's just uniformly old. This thing just must have just formed in one instant a very long time ago. It's really kind of cute. All right, so now to put this back in context of the black hole masses, this is bulge mass versus black hole mass and dispersion versus black hole mass. So the big star is where this thing lies. And so clearly this thing is consistent with an M sigma relation within the scatter, but it has a black hole that's way too big for its stellar mass, especially if you only count the central round thing as the center is bulge, then this does not check out. The other thing why this is interesting is we know that galaxies at a higher redshift are typically much smaller. And so this is from a paper from Astrofísica from a couple of weeks ago. This is from the 3D HST plus candles data, sort of the best data that we have on this topic right now. On the left, it shows you in blue and red shows you the passive and the blue galaxies, and the lines show you where the distribution lies. And on the right, it shows you the same thing for redshift 2.75. There's a whole bunch of panels in between, which I've cut out. And it shows you that the passive galaxies at redshift 3 and stuff are much, much smaller at the same mass than they are today. And 1277 would, in the plot on the left, because it lives at redshift 0, would lie at size of 1 kiloparsec and 10 to 11. It would lie outside of that locus. And so it's interesting that 1277 could just be one of the galaxies from that epoch that has just passively evolved and not done any merging since. So it would be a good way to sort of figure out actually like what these galaxies are and what they did. All right. There's much more similarities between these galaxies at redshift 2 and 1277 and the other compacts that are just like it. Here's a couple of examples shown is that the galaxies at redshift 2 are all very disk-like and very flattened, which is the plot on the right. They have similar luminosity profiles as 1277. And it's really like tempting to say that these things are just passively evolved from redshift 2. There's a paper by Msun and Tofter, which is kind of interesting, where he really goes through the argument is like, can the galaxies, the submillimeter galaxies that we see at redshift 3, 4-ish, that are forming stars very intensely, could those things turn into the passive galaxies we see at redshift 2? And that seems to check out if you assume a star formation epoch for these things for about 50 million years. And if that's true, then that you can really expect some of these things to persist until today. And if 1277 and one of them, you would expect like high alpha abundance and stuff. And this all seems to sort of check out, which is really cute. The other thing that is really cute about this is that so 1277, if you look at the stellar mass versus the dynamical mass versus the size, it sort of lies outside of the locus of the current day early type. So the plot on the left is from Atlas 3D, and 1277 is a big star. If you take its dynamical mass, then it lies outside of their zone of exclusion, and which would then indicate that it would actually have a much higher mass-light ratio than you would normally think. It would most likely would have a very bottom-heavy IMF. And this sort of nicely comes back to the trend that we think that the mass-light ratio, the bottom heaviness of the IMF, sort of traces with the dispersion. That's a plot on the right. And so we have a sort of a really cute way to sort of tie all these things together. But the more important thing is that for the high redshift galaxies, we only have very few. We actually have dispersions. So this is the plot from 2011. The gray stuff here is Sloan, so that's redshift 0. All the error bars are data at redshift like 1.5 to 2. And this is a galaxy which they've actually measured stellar velocity dispersions. You can see that those galaxies have much higher velocity dispersion or much higher dynamical masses than the galaxies today. The cute thing about it, if I then overplot my HET survey galaxies into the dispersion size plot, I end up having lots of them like it. And that's mostly because in that survey, the thing that I went for was the things of the highest rate of influences, which are the things of the highest possibility dispersions. So it's really cute. I have a whole bunch of analogs to these things today, which is really fun. And so obviously the next step is to then do follow-up and look at them in detail. And so I started a program to image them with HST and do deep PPAK IFU data. So this is HST images is 160. So these are all really compact galaxies at redshift 0. Like most of them are on this plot are about 10 to 11, are about 1 kiloparsec. And you can see in all of these are really old disks that, apart from one, doesn't seem to have any interactions going on. They're all really compact and they just all look very, very boring, which is exactly what you expect in this case. And to show you an example of one that doesn't lie in the middle of a cluster, let's go look at Macarian 1216. So that's that thing, little bobby thingy. This is a DSS image. There's nothing around it. It just lives in the boonies by itself. The HST images on like the central region of the galaxy shown there. The half-light radius is, again, about like 1.5 kiloparsec for this thing, which is somewhere inside that little box. So the galaxy is flat, and then it has like a really round extended halo around it. This is the top row is the PPAK kinematics when it comes up, and the bottom row is the dynamical model of this thing. And then you can play the same game as we did for 1277. You can ask, like, does this thing have a big black hole, or does it have a weird IMF, and this kind of stuff. And for this particular galaxy with this data, we get a sort of ambiguous result, which is a bit unfortunate, but it's okay. So this plot now shows you H-band mass-light ratio versus black hole mass. So the white one contours 1, 2, and 3 sigma. And so you can already directly see that at 3 sigma, we don't get a secure detection of the black hole mass. So the best fit black hole mass is, we can essentially only say that the black hole mass must be below 9.7. We don't actually get, or is it below, if you do 3 sigma error bars, below 10 to the 10. And your mass light ratio lies somewhere between 1 and 2.5, 2.3, which is unfortunate. And the reason this happens is because the galaxy is so tiny that the black hole and the stellar mass light ratio of the stellar body is essentially the same thing. Obviously the black hole has a round potential, the galaxy is flat, but they sort of operate on the same scale, so that's why you sort of don't get a direct thing. And to sort of make that point a little bit more clearly, this is the plot that shows you the mass distribution in these galaxies. So this is a little bit of a complicated plot, but the blue line here shows you the black hole mass and the upper limit. The the red line is the stellar mass distribution, so it's total enclosed mass as function of radius, and the dotted lines are then the error bars. And the green here is the best fitting dark matter halo and its error bars. The first thing that you need to notice is that we have data that goes out to 3-4 effective radii in this particular object. And at that radius, the dark matter halo is just not important. So you have this, which is sort of what you expect, because an NFW halo has a humongous core, and this galaxy is very dense in the center, so you don't expect the dark matter to become important at large radii directly. But it's interesting, because normally in the early types, you do expect it to become important fairly quickly. But more importantly, in the very center region, so the effective resolution of this data is about 0.6 kiloparsec. This thing lies at 110 megaparsec. And at that radius, the stellar mass and the inferred black hole mass are roughly equal. So essentially what happens is that at the resolution that we have in this case, you actually can't get the black hole mass, right? And this is one of the reasons why I started at the beginning. You need to get AO data to do this, right? And so this is another example. This is NG1271. This is another little disk thing in the bottom right corner. And for this one, we do have the HST image. We have Osiris KKO data on the bottom right, and we have really good PPAK data. And so this is, again, a really flat thing that rotates with a little bulge and stuff. And for this thing, we do actually get a black hole mass. This one is about 9.5 with a mass light ratio and H band of 1.3, which is actually, that mass light ratio is actually what you expect for a normal early type. So this one is interesting because it doesn't seem to have a very weird IMF or mass light ratio. All right, so this is, but it then again does have a very big black hole for its stellar mass. One more small point before I wrap up. I'm finding really big black holes in very compact, dense galaxies that are not the most luminous things either. But people are also finding black holes in galaxies in very small galaxies that don't have any bulges whatsoever. And this is also a big deal. If you think that the black holes somehow are connected to bulges, then these things shouldn't exist, but they clearly do. So if there's a direct connection between the bulge and the black hole mass, then then we. I don't know how to answer this one. And this is the other important point: is that this is from the Cormier and Ho review. This shows you all the references for where they get the black hole masses from. The thing to realize is the bottom right column is that they cite a bazillion papers that have all measured the black hole masses in a slightly different way. You need to be a little bit worried about this. But this is the most important one. Here, this is the standard fundamental plane parameters of galaxies, so it's dispersions versus luminosity and size. The gray contours gives you the number density of nearby galaxies, or whatever you want to do it. So the bottom left is the Faber-Jackson. And the crosses here are the black hole masses, so the galaxies for which you have black hole masses. And the thing to realize is that they are actually located in not very nicely with where the galaxies actually lie. So the galaxies for which you have black hole masses are not actually very representative for the galaxy population at large. This is something that we should try to fix. All right. And then I'll have my conclusion slide. So we need to figure out how black holes and galaxies actually link together, and we don't actually know that as well as we think we do. I have the right sample to go do this now, and I have a whole bunch of compact galaxies which are interesting for galaxy evolution properties and much more things as well at the same time. And that was it. Thank you.
Thank you very much for this nice talk. Time for questions.
So something that puzzles me and even worries me about this very complex leak, that is bigger galaxies in luminosity and I don't know in mass, but it seems that it's a small thing surrounded by a lot of things. So if it's really a relic of the Redshift 2 galaxies that we see, massive galaxies, very compact galaxies that we see at Redshift 2, at Redshift 2 we don't see the very compact ones. Well, all massive galaxies are more compact than local galaxies. Yes. And the ones that are more compact, we don't see things around. They are centrals. They are the main galaxy in the surrounding. Of course, the evolution can be dropping in some other part, but it seems that environment is very different in that guy as in Redshift 2 compact massive galaxies. So do you have any ideas why this could be, or maybe it's
well, really a lot of clustering still happens, right, since then. Like most galaxies of Redshift 2 still undergo a lot of evolution. There's a lot of minor merging and that kind of stuff. And for most galaxies, you expect that to happen. And but the more important thing to realize is that the number density of galaxies in Redshift 2 is much lower, like in general, than today, right? So you know that the galaxies that have formed since or evolved since are not the same galaxies most of the time. Like for 1277 might be one of the exceptions for which nothing happened. And so typically most galaxies do undergo a lot of evolution. And even more so that you can't really go directly compare one with the other. It's not really the way to do it. I guess that's the easy way out to your question.
Could you comment on the possibility that the 1277 is a stripped bulge, in the sense that it was maybe a Milky Way-like galaxy that lost the disk, because in fact it is very close to the very active galaxies, just 70 kiloparsecs from there.
It's not far away, that's right.
Could it be possible?
It's really hard to sort of prove that it was not stripped. Like it's very hard to do. The thing that you can do is, if your argument is like, well, it was stripped and that's why it has such a big black hole, then the galaxy around it that originally when it started must have been way, way bigger, right? That it must have been the biggest galaxy in Perseus. Right? Because it has the biggest black hole in Perseus, so it must have had the biggest galaxy around it.
Yep. Okay. Yeah.
And that doesn't mean it's in the strip, right? But the other thing about it is it does seem to have a dark matter halo around it, which if it would have been stripped, that would have been gone as well. But it's very hard to sort of make that point. And this is also why I showed Macarian 1216 as one of these things also existing that lives out in the boonies. It cannot have been stripped. But it's very hard to sort of disprove it. The other way to do it is, one of the ways to try to do it is the same argument as the dark matter halo, is count global clusters. That also works, which has not yet been run.
Okay, just a small question. Wouldn't it be possible that the bulges, as Alistair Graham said, bulges are similar to very compact galaxies in the sense they are as dense as them, and so they're very close.
Yeah, well, that comes back to the same point. Most galaxies undergo a whole bunch of evolution, and if that is what happens, then then you expect those things to be sitting at the center of most galaxies today. They do get puffed up a little, but that's okay. That comes in with the merging. Yeah.
I have actually. Could you show an image of this 1277, or because it seems well in the images? Okay.
You want to see the blow up, right?
No, it seems that it has a ring around.
The ring. That's just a color stretch.
Okay.
That's the same thing with all the other ones, right? It's just that's just DS9, the heat color map that you can.
Okay. And now.
Because this is the same thing here, right? They all seem to have rings.
Yeah.
Yeah, that's just the color map.
Okay. And this is something, different. It's about, are they all AGNs? And if so, what are the properties, X-rays, these kind of things?
None of them have broad emission lines. A couple of them have some emission lines, but most of those, almost all of these have like a tiny little dust disk in the center. And it seems that the emission that we do see is typically associated with that little bit of dust.
So are they AGNs or not?
Well, AGN is a very broadly defined term.
Okay.
They're not broadline AGN. 1277 and 1270 have some AGN, some X-ray flux. But for a 10 to the 9 solar mass black hole, at essentially any given accretion ratio, you would expect to see some X-ray flux. Does that make it an AGN? But they're not eating at a high rate. Let's put it that way. None of them are.
Okay.
Yeah, can you go to your last slide, or the previous to the one to the last, or the one where you show the distribution of velocity dispersions? And I understand this is from the literature, that data collected, or is your data?
So the gray stuff is essentially Sloan in the nearby volume, so that's representative number density. The black crosses are either the Cormandy or the Nicholas McConnell's
compilation of the literature. Okay.
Yeah.
So, do you think that the fact that they are not representative or they are biased somehow in those plots to being to have more compact sizes and higher velocity dispersion, that could maybe affect the relation we know between the black hole mass and the velocity dispersion? And do you think that maybe this relation is artificially having less scatter than it should have?
Well, or maybe more. The reason what happens is that because when people want to measure black hole masses, they first estimate a straight up influence to see if they can do it, which means they preferably end up picking galaxies with higher dispersions. So they end up picking, especially in this plot, they end up galaxies with high dispersions for whatever the thing is. So they end up all being the highest dispersion things. And a lot of these things that lie outside that locus in the bottom right of these three plots are typically galaxies that are, some of them are definitely stripped, like NZ4486b, and some other things are definitely like stripped things. The question, what happens to your M-sigma scaling relation when you just take galaxies on the locus, that's a pet project that I need to do ASAP.
Yeah, but my point is that, in the last 10 years, people have been using the supermassive black hole velocity dispersion relationship and the small scatter this relationship have to argue that this is implying a coevolution between these two completely different properties of the galaxy. So
the question is whether or not that scatter goes up or down when you remove those points. I do not know that answer. I want to know, but I do not know.
My point is that if that relation were having much more scatter, just taking representative galaxies, then nobody will have used that, and that will be not a puzzle anymore.
Right.
So I think it's really worth exploring this.
Right, but we already have that. Even without doing that, we already have that problem today, right? This is the M sigma today. At low dispersions, there's not a tight relation anyway. So this is, you need to worry about this a little. I completely agree.
So I guess the take-home message would be that we have to be more careful maybe about the M-sigma relation, but we cannot say, it doesn't work anymore, really, right?
We have work to do. Let's put it that way. We have some work to do to figure out what's going on. But you shouldn't take the M-sigma for granted, I guess is the bottom line. That's right.
For example, in relation with what Nacho said, we know that the supermassive black holes have some influence in the, for example, star formation history of the galaxy and things like that. So it's not like they are two complete independent entities.
Right. And we expect that the black hole feedback is what turns over the luminosity function, and so it's important. It's very important.
More questions? Then we can thank Remco again.
Thank you.